It's 2:14 a.m. in Penza Oblast, Russia. 10 thermal signatures appear 625 kilometers from the Ukrainian border. They're moving at 140 kilometers per hour toward one of Russia's most secure military facilities. But Russian radar can't see them. Not yet. The Polyana D4M1 facility sits in the heart of Russia's industrial zone. This isn't just another factory. This is where Russia builds the brains of its air defense network. The command systems that coordinate every S-300 and S-400 battery across the Western Military District. The facility operates behind 3 layers of electronic warfare protection, GPS jammers, acoustic detection systems, and counter-drone batteries that have stopped dozens of attacks before. Tonight, something is different. The drones flying toward Penza aren't like anything Russian defense forces have encountered. They're not the modified commercial quadcopters used in frontline attacks. They're not the kamikaze drones that hit fuel depots near the border. These are custom-built fixed-wing aircraft. Each one carries a 35-kilogram warhead. Each one is designed for one purpose. Deep penetration strikes into territory that should be unreachable. But reaching Penza means surviving 625 kilometers of hostile airspace. It means evading radar systems designed to track targets 400 kilometers away. It means overcoming GPS jamming so powerful it can disable satellite navigation across entire regions. And it means staying invisible to acoustic sensors that can detect engine sounds from 15 kilometers away. The mission began 6 hours earlier. Ukrainian engineers loaded 10 drones onto transport vehicles 40 kilometers behind the front line. Each drone carried a navigation package that included 3 backup systems: standard GPS for initial guidance, inertial navigation for when GPS failed, and visual recognition software that could identify targets from aerial imagery. The drones launched at 8:23 p.m. from a forest clearing. They climbed to 300 meters, formed into a loose formation, and turned northeast. The flight computers were programmed with 47 waypoints. Each waypoint marked a position where the drones would adjust course to avoid known radar coverage zones. At 9:15 p.m., the formation crossed into Russian airspace. Russian border radar detected nothing. The drones were flying too low and too slow to trigger automatic tracking systems. Their composite bodies reflected minimal radar energy, and their electric motors produced almost no heat signature when running at cruising power. But at 10:42 p.m., everything changed. A Russian GPS jamming station near Voronezh activated its transmission array. The electromagnetic pulse covered 200 square kilometers. Inside that zone, every GPS receiver stopped working. The drone's navigation system switched to backup mode instantly. But the backup wasn't perfect. Inertial navigation works by tracking acceleration and rotation. It calculates position by measuring every movement from a known starting point. It's accurate for short distances, but over hundreds of kilometers, tiny errors accumulate. A 0.1 degree drift in heading becomes a 5-kilometer positioning error after an hour of flight. The lead drone recognized the problem. Its flight computer detected the GPS loss and calculated the degradation rate of inertial navigation. At current drift rates, the formation would miss the target by 12 kilometers. That wasn't acceptable. So the lead drone did something unexpected. It shut down its engine. Without engine noise, the drone became completely silent. It glided on its wings, losing altitude slowly. Russian acoustic sensors detected nothing. The penicillin system, designed to track artillery shells by sound, registered only ambient noise. But gliding meant losing altitude. The lead drone dropped from 300 meters to 180 meters, then 120 meters. At 80 meters, it restarted its engine for 3 seconds, just enough to climb back to 200 meters. Then it shut down again. This pattern continued for 90 minutes. Engine on, climb, engine off, glide. The other 9 drones followed, maintaining formation through radio signals too weak to trigger Russian electronic warfare systems. At 12:33 a.m., the formation reached the Tambov region. They were 380 kilometers from the target. Russian air defense radar swept the area every 40 seconds. But the drones were flying at 150 meters now, below the radar horizon. Mountains and terrain masked their approach. Then the second defensive layer activated. A Russian Krasuka 4 electronic warfare system began broadcasting GPS spoofing signals. This wasn't just jamming. This was deception. The system transmitted fake GPS signals that told receivers they were 45 kilometers south of their actual position. Any drone relying on GPS would turn south, away from the target, thinking it was correcting course. The Ukrainian drones received the fake signals. Their GPS receivers locked onto the stronger Russian transmission. The navigation computers processed the coordinates, and according to GPS, the drones were now 45 kilometers off course. But the flight computers didn't trust GPS anymore. They hadn't trusted it since the first jamming station activated 2 hours earlier. The inertial navigation system was still primary, and the inertial system knew the GPS coordinates were wrong. Here's where the mission design became critical. Ukrainian engineers had anticipated GPS spoofing. They programmed the drones to ignore GPS data that conflicted with inertial navigation by more than 10 kilometers. The fake Russian signals showed a 45-kilometer discrepancy. The drones classified it as hostile deception and continued on their original course. At 1:47 a.m., disaster struck. 2 drones in the formation experienced motor failure. The cause was unknown. Possibly electromagnetic interference, possibly component failure from extended flight time. Both drones descended rapidly, crashing in forest areas 180 kilometers from the target. The remaining 8 drones continued. They were 250 kilometers from Penza now. Russian air defense forces had no idea they were coming. At 2:02 a.m., a Russian forward observation post reported unusual acoustic signatures. The report described low-frequency sounds consistent with small aircraft engines. The report was logged but not escalated. Russian forces received hundreds of similar reports every night. Most were birds, civilian aircraft, or sensor glitches. The drones pressed deeper into Russian territory. At 2:14 a.m., they reached the final approach corridor. Penza was 40 kilometers ahead. The facility's own air defense systems were active. 2 Panzer S-1 batteries provided close-range protection. Their radar could track targets at 30 kilometers and engage at 20 kilometers. But the drones weren't at 30 kilometers yet. They descended to 60 meters above ground level. At this altitude, terrain interference made radar tracking nearly impossible. Hills, trees, and buildings created radar shadows. The drones flew through these shadows, invisible to defensive systems. At 2:19 a.m., the formation climbed to 200 meters for the final approach. They were 15 kilometers from target. The Panzer radar detected them immediately. Targeting computers locked onto 8 contacts. Threat classification: unknown small aircraft. Engagement decision automatic. The Panzer system prepared to fire. But there was a problem. The engagement protocol required verification of hostile intent. Unknown aircraft could be civilian, could be friendly. The system needed 3 seconds of tracking data to confirm hostile trajectory. 3 seconds at 140 kilometers per hour meant the drones traveled 117 meters closer. Now they were 14.9 kilometers away. The Panzer radar operator watched his screen. 8 contacts, all moving directly toward the facility. Trajectory confirmed hostile. He authorized engagement. 2 Panzer batteries fired simultaneously. 12 missiles launched. Each missile carried a 20-kilogram fragmentation warhead. They accelerated to Mach 2.5, closing the distance in seconds. But the drones had one final trick. The lead drone, flying 200 meters ahead of the formation, suddenly began transmitting. It broadcast a GPS signal identical to Russian military navigation codes. The signal was strong, directional, and positioned to make Russian missiles think they were 800 meters south of their actual location. The Panzer missiles received the fake GPS data. Their guidance systems processed it, and because the signal used correct Russian military authentication codes, the missiles trusted it. They adjusted course south, chasing phantom targets that didn't exist. The lead drone's transmission lasted 4 seconds. Then it stopped. The Russian missiles, now off course, attempted to reacquire targets, but their radar seekers couldn't relock in time. 11 missiles detonated in empty air. 1 missile's proximity fuse triggered near the lead drone, shredding it with fragments. 7 drones remained. Distance to target 8 kilometers. The Panzer batteries attempted to reload. Reload time 8 seconds. At current drone speed, they would reach the facility in 206 seconds. The Panzer could fire again in 8 seconds, but targeting solutions took 3 more seconds. Total time before next engagement, 11 seconds. The drones would be at 3.6 kilometers by then. Well inside minimum effective range, Russian forces activated backup systems. Electronic warfare operators increased jamming power to maximum. The electromagnetic interference was so strong it disrupted Russian communications. But the drones no longer needed GPS. They no longer needed radio signals. They were running on final approach programming loaded before takeoff. Visual recognition systems activated. Onboard cameras compared ground imagery to pre-loaded satellite photos. Building layouts, road patterns, distinctive structures. The computers identified the target facility with 97% confidence. At 2:21 a.m., the drones began their terminal dive. They descended at 45-degree angles, accelerating to 180 kilometers per hour. Impact time, 24 seconds. Russian personnel at the Polyana facility heard the engine sounds. Alarm systems activated. Personnel ran for shelters, but there wasn't enough time. The first drone struck the northern manufacturing building at 2:21:24 a.m. The 35-kilogram warhead penetrated the roof before detonating. The explosion created a fireball that reached 600 degrees Celsius. Manufacturing equipment for command circuit boards melted instantly. 3 seconds later, the second and third drones hit the central assembly hall. The building collapsed inward. Flames spread through ventilation systems. Secondary explosions erupted as stored electronic components ignited. The fourth and fifth drones targeted the administrative complex where command system software was developed and tested. Both warheads detonated simultaneously. The building's reinforced concrete structure fractured. 3 floors collapsed into the basement levels. The sixth drone struck a transformer station that powered the facility. The electrical grid failed immediately. Backup generators activated, but the fire suppression systems had lost power during the critical first 30 seconds. Fires that should have been contained automatically spread unchecked. The seventh drone hit a storage warehouse containing completed Polyana D4M1. Command units ready for delivery to air defense batteries. 8 units worth 180 million rubles were destroyed instantly. The loss represented 6 months of production capacity. The facility's fire suppression teams responded within 4 minutes. But the fires had already reached critical intensity. The main manufacturing building's roof collapsed at 2:34 a.m. Flames reached 50 meters high. The heat was so intense it cracked windows in buildings 200 meters away. Russian emergency services arrived at 2:51 a.m. They found 3 buildings fully engulfed, 2 more buildings damaged by secondary explosions, and fires spreading to adjacent structures. The facility's strategic position, chosen for security, now worked against rescue efforts. Remote location meant fire teams had to travel from Penza City, 40 kilometers away. By 4:15 a.m., firefighters established containment lines, but the damage was catastrophic. The northern manufacturing building, where circuit boards were produced, was completely destroyed. The assembly hall, where components were integrated into finished systems, had collapsed, and the administrative complex, containing irreplaceable design files and testing equipment, was structurally unsound. Russian military command assessed the damage at first light. The Polyana D4M1 facility was Russia's only production site for these specific command systems. Each system coordinated air defense operations across regions covering thousands of square kilometers. The destroyed units were destined for deployment in western Russia, where they would coordinate S-300 and S-400 batteries defending against NATO airspace. Without these command systems, Russian air defense batteries operated in isolated mode. They could still fire missiles, but coordinated response across multiple batteries was degraded. Radar data sharing was reduced. Threat assessment was slower, and engagement prioritization was localized instead of regional. The strategic impact extended beyond hardware. The software development center was destroyed. The engineers who programmed threat libraries, engagement algorithms, and coordination protocols lost years of work. Backup systems existed, but they were months out of date. Current threat databases, updated with data from the ongoing conflict, were gone. Ukrainian military intelligence confirmed the strike's success through satellite imagery captured at 9:30 a.m. Analysts identified 7 impact craters, 3 collapsed buildings, and thermal signatures indicating fires still burning 12 hours after the attack. Damage assessment classified the facility as non-operational for a minimum of 8 months. The cost calculation was striking. 7 drones at approximately $58,000 each. Total mission cost, $406,000. Damage caused, estimated at 340 million rubles in destroyed equipment, plus incalculable operational degradation of Russia's Western air defense network. The asymmetry was profound, but the real achievement wasn't economic. It was psychological. The Polyana facility was 625 kilometers from the Ukrainian border. It was protected by multiple layers of electronic warfare systems. It had dedicated air defense batteries, and it was deep inside territory that Russia considered completely secure. The successful strike demonstrated that distance no longer provided protection, that electronic warfare could be overcome, that sophisticated defense systems could be deceived, and that even Russia's most secure military facilities were vulnerable to precision strikes using relatively inexpensive drones. Russian military command immediately ordered security reviews at similar facilities across the country. Additional air defense batteries were redeployed from frontline positions to protect industrial sites. Electronic warfare systems were reconfigured to counter the specific tactics used in the Penza attack, but each defensive measure pulled resources from the active combat zone. The Penza strike represented a fundamental shift in modern warfare. It demonstrated how small, expendable drones could achieve strategic effects, previously requiring aircraft, cruise missiles, or special operations forces. It showed how creative tactics and advanced navigation could overcome superior defensive technology, and it proved that in modern conflict, distance and fortification no longer guaranteed security. The mission's technical sophistication revealed months of planning. Engineers had reverse-engineered Russian GPS spoofing protocols to create countermeasures. Intelligence analysts had mapped radar coverage zones to identify flight corridors. Programmers had developed navigation algorithms that could function without satellite guidance. And mission planners had identified the vulnerability windows when defensive systems were least effective. This wasn't a random drone attack. This was precision engineering applied to strategic warfare. Every element of the mission had been calculated, tested, and optimized. From the engine shutdown sequences that evaded acoustic sensors to the GPS spoofing that deflected interceptor missiles, the operation demonstrated how careful analysis could turn technological disadvantages into tactical advantages. The 7 drones that reached their target had flown further into Russian territory than any previous Ukrainian strike. They had overcome defensive systems designed to stop exactly this type of attack. And they had achieved their mission objective with a success rate that exceeded even optimistic predictions. If you want to see more precision strikes and tactical breakdowns, hit subscribe, there's more coming.